Hello students, we have discussed about the constructional details of DC machines and working principle as generator and motor. Today we will see that how exactly the DC characteristics we are going to classify. So the DC motor characteristics are classified mainly into electrical characteristics and mechanical characteristics. So electrical characteristics mainly what we are going to consider is torque versus the armature current. The armature torque versus armature current, and then one more characteristic we are considering, that is speed versus armature current, and the mechanical characteristic we are considering, that is speed versus torque. So how exactly the torque varies with respect to armature current, how exactly the speed varies with respect to armature current, how exactly the speed varies with respect to the armature torque, you are going to see now for the different types of motors, that is series, shunt and compound motors. For this mainly we are going to consider the equations what we have derived already, the EMF equation and the torque equation. You see that we know that the EMF equation EB is equal to Zn phi p divided by 60A. From this we can see that EB is directly proportional to speed N, and then we have one more equation, that is EB is equal to V minus IA RA in case of shunt motor. In case of series motor, this is RA plus RAC, because the series field winding is connected in series with the armature. So this is EB is equal to V minus IA RA plus RAC in case of DC series motor. So in this case, what is this IA? IA is equal to V minus EB divided by RA plus RAC, or if it is shunt, you will have only RA, because in case of shunt motor, the shunt field winding is connected in parallel with the armature. So IA is equal to V minus EB. So with respect here, only EB is variable. So V is fixed and the resistance is fixed. So then with respect to this EB, IA will vary, and EB is directly proportional to speed. And one more equation you have, that is with respect to torque, this is equal to EB into IA. See, in this case also, this torque, armature torque is directly proportional to armature current IA. So this is divided by 2 pi N divided by 60. As you observe in this, TA is inversely proportional to speed and directly proportional to IA. This we have, that is 9.55 times EB IA divided by N. So by considering these equations and also the one more equation of TA, that is 0.159, that is phi Z IA in terms of Newton meter, there are two equations for torque, and then there are two equations for EB, that is EB is equal to Zn phi p divided by 60A and EB is equal to V minus IA RA. By considering all these equations, the relationship between this torque versus IA, the speed versus IA and speed versus TA is plotted. Okay. So this is the electrical characteristic and this is the mechanical characteristic of motor. Now you see that how exactly these three characteristics you are going to get in series motor, shunt motor and compound motor. Now when we are considering this DC series motor, we know that this EB is equal to Zn phi p divided by 60A, and also in case of this DC series motor, when we are going to connect, so this is the way how exactly we are connecting. This is the armature, and in series with the series field winding we are going to connect. Here we are going to give the supply. So current I will flow in this way. So this is same as this ISC, that is the current flowing through this series field winding and also the current flowing through armature, because the armature series field winding are connected in series with this supply voltage. That is why I is equal to ISC is equal to IA. the flux produced due to this IAC and then flux produced due to this current IA. So, that will be now torque is directly proportional to phi into IA according to this relationship. You see that TA is directly proportional to phi into IA. Since this is connected in series, as current I varies, what will happen? The flux produced in this coil also varies. That is why TA is directly proportional to phi into IA. The remaining things are constant. This 0.159 is constant and the number of conductors are constant. So, TA is directly proportional to phi IA, and this phi is also directly proportional to this IA because this IA is equal to IAC. So, now what is this equation represents now? Now, TA is equal to TA is directly proportional to IA square. How it looks like? So, now when you are considering this characteristic, you see that it's torque versus current IA. See, torque is directly proportional to IA square. So, the torque varies, that is with respect to current IA in the relationship, that is TA is directly proportional to IA square. This is the way we are going to get the characteristic. We know that shaft torque, the whatever we are getting this armature torque, it is not fully available at the shaft due to frictional losses. That is why you have it is TSH in this format. Okay, it is always less than the armature torque. This is about the torque current characteristics of DC motor. Next you see that this is the speed and current characteristic. See here, we know that EB is equal to V minus IA into RA plus RSE. Here IA is equal to V minus EB divided by RA plus RSE. So, here EB is equal to what? V minus, that is Zn 5P divided by 60A, this divided by the resistance, this is RA plus RSE. See here IA, now the speed relationship and then IA is due to this back EMF EB. Okay. So, you are going to get the characteristic, that is N and IA, that is because of this characteristic N is directly proportional to EB by phi. So, this current here we know that phi is directly proportional to IA, therefore, speed is directly proportional to EB by IA, means what? The speed is inversely proportional to IA. The speed is inversely proportional to IA. That is why we are going to get the characteristic like this, that is speed is inversely proportional to current IA. And then you see the mechanical characteristics of DC series motor. So, that is, this is the combined characteristic of this. Here you have the torque versus IA, speed versus IA. Now, what you are considering? The speed versus TA. So, the speed versus TA is the combined characteristic of these two. You can obtain this speed versus TA by using the characteristics of TA versus IA and speed versus IA. So, and also we have seen that in this, that is the TA is inversely proportional to the speed, means the armature torque is inversely proportional to the speed. So, the inverse characteristic is represented in this manner. Okay. These are the characteristics of DC series motor, that is first one is torque versus armature current, next one is speed versus armature current, and third one is speed versus torque. From these we know that the DC series motor is high, it has high starting torque. So, that is why it is applicable. So, when we are seeing these applications of DC series motor, we have to see that what exactly the advantage of this DC series motor. This DC series motor has high starting torque and quick acceleration. That is why this DC series motor is used in traction application, hoist and lift application, crane application, rolling mills and conveyors. This is about the characteristic of DC motor and applications of DC motor, particularly DC series motor. Now you see that how exactly you are going to get the characteristic for DC shunt motors and also what are the applications. This is how we have the connection of DC shunt motor. As the name indicate, it is the shunt field coil is connected in parallel with the armature. The armature resistance, the small value of armature resistance is represented in this. So you can represent with the small resistor value or otherwise. So if you are not representing also, it will indicate that this armature is having the internal resistance which is of very small value. Okay, the shunt field winding is connected across the armature, and then the supply is given. So IL, that is the current drawn by this armature. This IL is equal to ISH plus IA. So now when you are going to consider this, so first you see the equations, that is considering for this the similar equations you are going to consider, that is EB is equal to Zn 5P divided by 60A. EB is equal to Zn 5P divided by 60A. In case of this, phi is constant because ISH is constant. Because we know that ISH is equal to V, the applied voltage divided by RSH. Here the applied voltage is constant and this resistance of the shunt field winding is constant, that's why this ISH is constant. So in this case, so EB varies with only this speed. Okay. So now, and also we have that TA is equal to 0.159 phi ZIA. In this, the number of conductors are constant, phi is constant, so TA is directly proportional to IA. It varies linearly with respect to IA. So that armature torque varies linearly with respect to IA. You see this characteristic? How exactly you will get it? See, torque varies linearly with respect to IA, or IA varies linearly with respect to torque because torque is directly proportional to IA. As I already told you that full armature torque is not available at the shaft, so due to frictional losses, so shaft torque is always less than the armature torque. Next you see the characteristic. Here the speed is, when the speed increases, what will happen? Here the current decreases. So this is inversely proportional. So you can see that, and also you can think that the practical application in our real life. So without any load on our head, we can run fast. Suppose if you are keeping one bucket or one basket of apples on our head, what will happen? We can't run fast. So when we don't have any load on our head, we can run fast. But if we have some basket of apples, that full basket of apples, we can't run fast. So this is also, it is applicable in case of this speed versus current characteristic. What will happen? As the load increases, the speed decreases. So as the load decreases, the speed increases. So this is because here we have the characteristic equation, that is EB is equal to V minus IA RA in this case. So that is IA is equal to V minus EB divided by RA. So now EB is equal to what? This is Zn 5P divided by 60A. So according to this relationship, we have the speed is, as the speed increases, the armature current, as the armature current increases means the load increases, the speed decreases. So now you see the characteristics of shunt motor, that is speed versus TA. We know that always the TA is, when we are considering this relationship, that is EBIA, that EBIA is what? Here the TA is equal to, that is 9.55 EBIA divided by N. So in this you can see that TA is inversely proportional to speed. So that inverse proportionate is shown in this. Okay. So speed varies, that is speed is inversely proportional to torque, or torque is inversely proportional to speed. So according to these characteristics and the advantages of the shunt motors, So, these motors are constant speed motors, hence used in applications requiring constant speed. Almost it is constant, you see that it won't vary much. Here the speed is always, it is almost constant. So, it is not, see here, the speed is always constant because due to this IARA drop, so and also EB, V minus EB, so you are going to get that only that few values here you have that drop in this, the speed. So, that is why it is called it as the constant speed motor. So, that is why these motors can be used in lathe machine applications, drilling machine applications, grinders applications, blowers applications and compressors applications. All are applicable to this constant speed motors. So, next you see how exactly the characteristics of DC compound motors. This DC compound motors means here the way in which the series field winding and shunt field winding is connected. So, depending on how exactly it is connected, so you are going to divide this into differentially compound and cumulatively compound motors. See here, in this the shunt field winding is connected across the series combination of the series field winding and then this armature. This is called long shunt. If it is connected only across the armature, this terminal is shifted here. So, that is called short shunt. And this, how exactly you are going to differentiate, it is cumulatively compound and differentially compound. The flux produced due to current flowing through this shunt field winding and the flux produced due to current flowing through this series field winding, both are in the same direction, then it is called as cumulatively compound motor. If the flux produced due to current flowing through the shunt field winding and the current flowing through the series field winding, both are in the opposite direction, then it is called as differential compound motor. So, now you see that this, since you are connecting this shunt winding and also this series winding, these characteristics of compound motors can be obtained by the combined effect of the DC series motor characteristics and DC shunt motor characteristics. That is why I have compared this series motor and shunt motor with this cumulatively compound and differentially compound. See, this is the characteristics of torque versus IA in case of series, and the shunt motor characteristic is this. It is, we know that TA is directly proportional to IA square in case of DC series motor, TA is directly proportional to IA in case of DC shunt motor. In case of cumulatively compound, we know that the flux produced due to the current flowing through DC series winding and then the shunt winding, both are in the same direction. That is why you are getting, this is the characteristics of cumulatively compound motor, that is torque versus IA. In case of differentially compound, the flux produced in the series winding and the flux produced in the shunt winding, both will be in the opposite direction. So, this is the way you are getting this torque versus IA characteristics in differential compound motors. Next, you see that speed versus IA characteristic. So, we know that this is the characteristic of, that is speed versus IA in case of DC series motor, and since this DC shunt motor is of constant speed motor, this is the characteristics we are going to get. In case of cumulatively compound, this is the characteristic for speed versus current, and differentially compound, this is how you are going to get the characteristic for speed versus IA. Next, you see that the mechanical characteristic, that is speed versus torque or torque versus speed. So, now also you compare that series characteristic, shunt characteristic, and also you compare these two with differential and cumulative. This is how we are going to get the speed versus torque characteristics in case of DC series motor, and this is the characteristic in case of DC shunt motor, and then the flux produced in the field windings, that is series field winding and shunt field winding, both are in the same direction in case of cumulatively compound motor. That is why we are getting the characteristic like this. In case of differential, the flux produced in the series field winding and shunt field winding, both are in the opposite direction. So, this is the way you are going to get that the characteristics of speed versus torque in case of differential compound motors. Now, you see the applications of cumulatively compound motors. So, since the series field winding is connected in series with the armature, these motors also have high starting torque. They can be operated at no load as they run at a moderately high speed at no load. Hence, these motors are used for the following applications. That is, it is used for elevators applications, rolling mills applications, punches, shears and planners. And you see the application of differentially compound. So, here the speed of these motors increase as load increases, which leads to an unstable operation. So, when the machines are giving that unstable operation, these machines are not suitable for any particular practical applications. That is why normally we are going to use this cumulatively compound motors in practical applications. We are not going to use this differentially compound motors in case of practical applications. This is how you are got this characteristic of DC series motor, DC shunt motor and DC compound motors. Mainly you have the three types of characteristic, that is torque and armature current characteristic, it is called it as electrical characteristic, speed and armature current characteristics, that is speed versus armature current, and then speed versus torque characteristic, this is called it as the mechanical characteristic. We know that this by combining this 1 and 2 we can get this mechanical characteristic. So, and also we are using the important equations, EB is equal to Zn phi p divided by 60A, EB is equal to V minus IARA, TA is equal to 0.1595 Z IA into P by A, and then we have one more equation for TA, that is 9.55 EB IA divided by N. So, in this we can see that EB is directly proportional to speed, and then here TA is directly proportional to phi and IA, and TA is inversely proportional to speed. By using these relationship, we have got the characteristic for series motors, then shunt motors, and then the compound motors. Compound, it is cumulatively compound and differentially compound, and you have seen the applications also. So, this is about the operation of DC motors. Okay. Now, you see that there is one more thing is required in DC motor to start, that is the starter. Why it is required? So, what is the need of this starter? So, whenever the DC motor starts, it requires a current that is equal to, that is 5 to 6 times of its load current. But if you are not using the starter at the time of starting, since EB, the back EMF is equal to 0 and then the speed is equal to 0, there will be inrush of current. You have to avoid this inrush of current, that is why you are going to use a series resistance in series with the armature. What is the meaning of starter now? It is a variable resistance, it is connected in series with the armature at the time of starting, that is why it is called it as starter. So, we require only 5 to 6 times of its current to start, that is required to reduce the voltage when the motor starts. This job is done with a starter. What is starter? I already told you that it is a variable resistance in series with the armature circuit. Its work is to reduce the starting voltage up to such a value so that the increased current does not burn the armature windings. When the current increases, what will happen? All the armature windings will get damaged. That is why to avoid that one, you are going to use that series resistance with the armature. As the rotating armature of a DC motor picks up speed, what will happen? The back EMF will be induced. Since the back EMF is induced, what will happen? Here, this IA is equal to V minus EB. As EB increases, this IA decreases. At the beginning, this EB is equal to 0. When EB is equal to 0, what will be the current IA? IA is equal to V divided by RA. So, what will happen if you are not increasing the resistance? What will happen? The current will be more. So, to avoid this inrush of current, you are going to add the resistance in series with this. So, now what is IA at the beginning? IA is equal to V divided by RA plus the starter resistance. So, what will happen as the motor picks up the speed, this EB increases. So, in this case you are going to reduce this RST, and then when the motor picks up the full speed, what you are going to do is you are going to make this RST is equal to 0. Next, I is equal to V minus EB divided by RA. This is the concept of starter. At full speed, the motor starts running normally. The job of starter finishes here. In other words, the starter offers resistance during the starting of the DC motor only to avoid the large current. At full speed, the starter is electrically out of armature circuit of the motor. Means you are going to consider it is cut in and cut out. So, cut in means the full resistance is included. Cut out means you are going to make that resistance is equal to 0. At the time of starting a DC motor, the back EMF, I already told you that back EMF is 0. Since back EMF is 0, what will happen? We are considering EB is equal to Zn phi p divided by 60A. Since back EMF is equal to 0, the speed is also 0. See the relationships in case of the DC shunt motor and DC series motor. We have that V is equal to the applied voltage is equal to the back EMF plus the armature resistance drop EB plus IARA for shunt motor. In case of series motor, we are going to add that series field winding. So, that is why this is V is equal to EB plus IA into RA plus RAC for a DC series motor. And you see that from these two equations, we can derive the equation of IA, that is IA is equal to V minus EB divided by RA for DC shunt motor. IA is equal to V minus EB divided by RA plus RS for DC series motor. So, now when EB is equal to 0 during starting, what will happen? IA is equal to V divided by RA for DC shunt motor. IA is equal to V divided by RA plus RS in case of DC series motor. So, when you are observing these equations, when AB is equal to 0, the current will be more at the time of starting. You have to avoid this inrush of current. So, that is why in this example you see that here we have considered that V is equal to 400 volt, then it is developing at this power, that is 20 kilowatt DC motor with a total resistance of 0.5 ohms. If the motor is directly connected to the supply, it will draw a current of how much? The applied voltage 400 divided by 0.5. See here, it is 800 amperes. The full load current of the same motor is only 64 amps. We require only 5 to 6 times of the 64 amps, but you see that we are getting the 12.5 times of the 64 amps. So, how do you get this? This is 20 kilowatt divided by this 400 volt will give you the current, that is, so you are going to get only 64 amps when you are calculating. So, it is 400 divided by 0.5, how much you are getting? It is 800 amps. Instead of getting 5 to 6 times, we are getting the 12.5 times the full load current. What will happen? This gives rise to heating and mechanical forces of 150 times full load values. This is very dangerous for the windings of the machine. So, that is why, so you have to must and should you have to provide the starter for DC motor. The problems of heavy inrush current at the starting time are these. Okay, you see what are the effects of this inrush of current? That is heavy sparking at the commutator and even flashovers. It may damage to the armature windings, damage to the rotating parts of the motor, large dip in supply voltage. So, to avoid all these things, what you are going to do? You are going to use the DC, that is starter for DC motors at the beginning of or the starting of the motor. Hence, for the protection of motor from high currents during starting period, say 5 to 10 seconds, within this 5 to 10 seconds, it is necessary to provide this starter, means you are going to connect a high resistance in series with the armature of motor at the starting period. The resistance should gradually cut in steps as the motor gains speed, and afterwards it is going to gradually cut out. Okay. So, that is why this starter is essential for DC motors. Now, you see that how exactly we are going to connect this. Before going to this 3-point starter, I am going to explain the simple connection of how exactly we are going to introduce the series resistance in series with the armature for different types of motors. how exactly the series motor connection is there? Here you are going to connect the armature, or you can represent it as M, AA, these are the two terminals. So, here itself if you are representing, that is RA, not necessary to represent here externally, here itself you can represent, or otherwise you can represent externally. And then what you are doing is, you are going to connect a variable resistance, this is R starter, variable resistance in series with this, and also the field winding you are going to connect, this is RSC. This is how you are going to do the connections of the starter in case of DC series motor. When the supply is given, current I will be flowing in this, that is also equal to ISC, that is also equal to IA. What will happen if you are not considering this RST? What will be the current IA? Here the back EMF EB you are going to consider, it is V minus EB divided by RA plus RSC. At the starting point, we know that when the motor is starting, EB is equal to 0. What is the equation of IA now? IA is equal to V divided by RA plus RSC. We know that RA and RSC both are of very small value, it is less than 1 ohm. So, what will happen if it is 250 volt? 250 divided by 1, IA will be 250 ampere. So, that is why what we are going to do is, we are going to add a series resistance, that is the starter resistance in series with this RA and ISC. What will happen now? As this RST increases, the IA decreases. This is how we are going to protect the series motor. Now, you see in case of shunt motor, how exactly we are going to do it. In case of shunt motor, this shunt field coil is connected across the series combination of this, it is connected across the series combination of starter resistance and then this motor, that is the armature. Okay. In the beginning, if you do not have this, what will happen? You see that current IA is equal to V minus EB divided by RA. Since EB is equal to 0, this is V divided by RA. There will be more current at the time of starting. That is why what you are going to do is, you are going to add this RST like this. This is a variable resistor. At the starting, this will be maximum. When the motor picks up its full speed, what will happen? This is going to cut out. This will become 0. Okay, this is how you are going to protect the motor, that is motor windings in case of shunt field winding. In case of compound motor, what you are going to do? So, shunt field winding you are going to connect, and then here the series field winding you are going to connect, and then in series with this you are going to add this starter resistance. So, this will be RSC. So, now in this case, that IA is equal to V minus EB divided by RA plus RSC plus RST. If you are not including this at the starting, since EB is equal to 0, what will happen? This is V divided by RA plus RSC. So, there will be inrush of current because the total resistance is almost equal to or less than 1 ohm. So, that is why what you are going to do is, you are going to include a large value of resistance in series with this, that is RST, to reduce the inrush of current at the starting. We require only 5 to 6 times the full load current at starting. It should not increase beyond this. So, that is why you are going to use the starter in series with the armature to avoid the damage of armature windings. So, this is the need of starter in case of DC motor. Now, you see that one specific starter what we are using is 3-point starter. Why it is called it as a 3-point starter? To give any name, it should be some reason, no? So, here you see that I will explain to you this constructional feature. Here the DC supply is given. So, here the field winding. This mainly we are going to use this 3-point starter to the shunt motor or compound motor. You see that shunt motor here armature is connected across this shunt field winding, or this shunt field winding is connected across the armature. Here A1, A2, F1, F2. This is the shunt field winding and this is the armature. This shunt field winding is connected exactly parallel to this armature, and then the supply is given from here. Here you see that there are 3 terminals L, F and A. So, this L is connected to the positive polarity of the supply, this F is connected to the field winding, this A is connected to the armature. Since there are 3 points, that is 3 main points L, F and A, this is called it as 3-point starter. And also there are some contact points. So, that is these contact points is full resistance is integrated into sections, and these sections we are going to consider it is some points here. These are called studs, and also these are called contact points. So, here we have 5 contact points as you see here, it is off, stud 1, 2, 3, 4, 5 and then run. These are called contact points and also the stud. Okay. And you see the construction here, here the L is connected to this overload release. This is the electromagnet. Here we have 2 electromagnets. This is one electromagnet, another one is this. Here we have connected to this field winding. This is called it as no volt coil. There are 2 electromagnets, one is for no volt coil, another one is for overload release. So, here we have that lever, this is the conducting part we have, and then here you see that this overload release coil, here we have connected to the conductor lever, and at this point at the bottom end of this lever it is there is a spring. This spring is attached to this conducting lever and another end is freely movable here. So, and also the soft iron piece is attached to this. What will happen when this, and also this conducting lever will move in this direction against the force of this spring, and then this spring is having that capability, because of its own force it can bring back when the current is not flowing. Okay. So, this is how this works. So, what will happen when the supply is given? So, here it is due to this force of this spring, this starter moves from this off position to stud 1. See here, in this case if you are seeing from this side, this resistor is fully included in series with the armature. So, and when this stud moves from this off position to this stud 1, and also one more parallel path is created, that is you observe in this, due to this no volt coil, the coil is connected in series with this field winding. So, when this conducting handle or starter handle moves from off position to the stud 1, there will be another parallel path created in series with this field winding. So, and then what will happen, due to current flowing through this field winding, this coil will be excited, and then this attracts this soft iron. So, then this handle moves from stud 1 to 2, 2 to 3, 3 to 4, 4 to 5 and then to run. So, what will happen at this point, this motor gets that it will run at full speed, means the EB will be more, that is V minus EB divided by RA, then the current you are going to limit. So, this is how this 3-point starter will work. So, in the construction it has one full variable resistor, this is integrated into different sections, and the contact points you are going to call it as stud. You have 7 contact points in this, off, stud 1, 2, 3, 4, 5 and then run. Here there are 2 electromagnets, one is no volt coil and another one is for overload release. Okay. So, when the supply is given, what will happen? So, this coil will be energized, and then due to the force produced in this starter handle will move from off to 1. And since one more parallel path is created in this, what will happen? The current will flow in this. Due to current flowing through this field winding, this coil will be energized. This will attract the soft iron. So, what will happen? This will move the position from 1 to 2, 2 to 3, 3 to 4, 4 to 5 and then 5 to 6. Means what? It is going to cut out, means remove the resistance. When the motor gets that full speed, what will happen? This RST will be equal to 0. It holds until any disturbance with the power, means if there is the current flowing through this is equal to 0, what will happen? This will go back due to this action of force of the spring. That is what here I had given in this theory. Whatever I have explained in this, that is given in this. You see that construction wise, a starter is a variable resistance integrated into number of sections, as you have already seen in the figure. The contact points of these sections are called studs and are shown separately as off, 1, 2, 3, 4, 5 and run. The other than that, there are 3 main points, that is, one is line terminal, another one is armature terminal, another one is field terminal. That is why this starter is going to call it as 3-point starter. The point L is connected to the electromagnet called overload release. The other end of overload is connected to the lower end of the conducting lever of starter handle, where a spring is also attached with it, and the starter handle contains a soft iron piece housed on it. This handle is free to move. As you see, this handle is free to move, one is fixed and the another handle is, this another side of the handle is free to move, that is from off to on. So, this handle is free to move to the other side, that is run against the force of spring. This spring brings back the handle to its original off position under the influence of its own force of the spring. Another parallel path is derived from the stud 1 given to the another electromagnet called low volt coil, which is further connected to the terminal F. That is what here. Here stud 1 2 and then this no volt coil 2, this field winding and also this terminal F. The starting resistance at the starting is entirely in series with the armature. The OLR, the overload release and no volt coil acts as these 2 protecting devices of the starter. So, when you are going to consider this working, so it will be in the beginning it will be in the off position. When the supply is given to the DC motor, the handle is slowly moved against the spring force to make a contact with stud 1. At this point, field winding of the shunt or the compound motor gets supplied through the parallel path provided by the starting resistance through no volt coil. When the no volt coil is energized, what will happen? The soft iron will move towards that no volt coil electromagnet. While entire starting resistance comes in series with the armature, the high starting resistance, the high starting armature current thus gets limited as the current equation. Since you have included this RST in series with that, the current IA will be increased, because current IA is inversely proportional to resistance. As the resistance increases, the current IA decreases. As the handle is moved further, it goes on making contact with that 1 to 2, 2 to 3, 3 to 4 and 4 to 5 and then to run. So, what will happen when the armature circuit of the motor gathers speed? Finally, when the starter handle is in run position, the entire starting resistance is eliminated, means you are going to make this RST is equal to 0. At that time, IA is equal to V minus EB divided by RA. So, we know that as the speed increases, the back EMF also increases. So, consequently, it reduces the armature current. So, the external electrical resistance is not required at that time. So, what will happen? You are going to make that resistance is equal to 0. As long as the supply to the field winding is there, then what will happen? It will attach to that run. Otherwise, what will happen? It has to go back to that off position. That is what it is given in this. So, the NVC, the no volt coil, is designed in such a way that it holds the handle in run position against the force of the spring as long as supply is given to the motor. Thus, no volt coil holds the handle in the run position and hence also call it as hold on coil. So, NVC is also called it as hold on coil because it holds the So starter handle in the run position. Now when there is any kind of supply failure, what will happen? The current flow is 0 through this NVC. So what will happen? It immediately loses its magnetic property and is unable to keep or hold the soft iron piece on the handle, that is, which is attracted by the electromagnetic field. At this point, under the action of the spring force, the handle comes back to the off position back. So it was in this run, then what will happen when current flowing through this is 0? So the electromagnetic effect will be lost. So it will go back to this off position due to its own force of the spring. So this is how the 3-point starter works. So what do you mean by this starter now? Starter is a variable series resistance. It is connected in series with the armature to avoid the inrush of current, to protect the windings of the motor and also the commutators. So this is up to this we have seen that how exactly the DC motor, DC generator works, the constructional features and then working principle, and then we have derived the equation of back EMF, we have derived the equation of torque, we have derived the equation of speed, and I have solved some more problems on this. So few problems I have already solved. I have solved most of the problems on shunt motor. So now I thought that I can solve some more problems on series motor and also the different variety of problems in shunt motor. Okay. So now, so all the concept I have explained, okay, of DC machines as generator and DC motor. So now we will solve some more problems on this. So to make you understand, I am taking the examples of this DC series motor and also I will take some examples of DC shunt motor also. You see in this problem, it is defined that it is a 4-pole machine. So P is equal to 4. So V, that is applied voltage is 250 volt. It is a series motor and has a wave connected armature. In case of wave connected armature, the number of parallel paths is equal to 2 with Z is equal to 200 conductors. The flux per pole is 25 milliweber. When the motor is taking 60 ampere, means the current drawn by this supply is 60 ampere. The armature resistance is this 0.15 ohm, while the series resistance is 0.2 ohm. Calculate the speed under this condition. See here, speed EB is equal to, we know that Zn 5P divided by 60A. If you find out this EB, so you can easily calculate that the speed of the motor. So now use this relationship. So collect the data given. So the data given is V is equal to 250 volt. P is equal to 4, Z is equal to 200. Since it is wave connected, A is equal to the number of parallel paths is equal to 2. Then phi is equal to 25 milliweber, means 25 into 10 to the power minus 3 Weber. Since this is series motor, the series field winding is connected in series with the armature. So RA and RSC both are in series and current IL is equal to ISC is equal to IA because it is connected in series. So IA is equal to IL is equal to ISC, that is equal to 60 amps. So now you use this equation, EB is equal to V minus IA, the total resistance RA plus RSC. The drop across this resistance you consider and then calculate EB. Substituting the required values, you will get that EB is equal to 229 volts. Now use this equation, that is the relationship between speed and back EMF, that is EB is equal to Zn 5P divided by 60A. So here EB is known, you have already calculated, Z is given 200, then N is unknown, phi is 25 milliweber, P is equal to 4, 60 into 2, A is the number of parallel paths, that is equal to 2. In this case, you are going to get the speed of the armature is equal to 1374 RPM. So this is how you have to solve the problem. I will solve the next problem in the next class, and also I am going to solve the few more problems on DC motor. Tomorrow I am going to end this DC machine in module 2. Okay. Next I am going to start that measuring instruments. So next class I am going to solve the more problems on this DC motor. That is the variety of problems with DC series motor and DC shunt motor. Thank you very much.